So we'll see how this works out. All right. So from here, open up your Jupyter notebooks. Make sure that you have Git pulled, the latest push. The latest push was like maybe an hour ago or so. Yeah, we're just going to run through a little bit of the stuff I was talking about in that presentation. So the first thing you should run is the stop cell. It just imports like the basic boilerplate. You've done it every time. And I'm going to go over this cell block that Joseph brought up last time. So basically, it's just running through all the possible k nearest neighbors values, or like a set of k nearest neighbors values. And I just wanted to ask you guys which of these could be like overfitting, underfitting, or like are pretty close to classifying it correctly. So in regards to these first two, like what do you think is happening? What is it, overfitting, underfitting, or is it like pretty close to guessing? Somebody say it or raise your hand or something. Overfitting? Yeah, it looks like it's overfitting. You see there's like a bunch of these blobs here, and I mean, it seems like it matches these values here correctly, but there's also the possibility that they are erroneously placed there. Like data collection may be problematic, and that's something just to keep in mind whenever you're dealing with data. Is that like any part of the process in actually making the data could be problematic as well. So you've got to leave some leeway, and then like you could probably expect that something around this range, k equals 15 and k equals 50, somewhere in between here, we'd probably get a probably accurate model of what's happening in there. We'd probably get like a solid boundary line. And I think k equals 50 is probably the closest to the correct classifier. But if we see in k equals 100, a lot more points are kind of overlapping, and we could expect that this is actually a case of underfitting. All right, now back to cross-validation. So the data set we're going to be dealing with is the digits data set. It's like kind of a toy data set that's stored in sklearn. It comes prepackaged in. The way to load it is basically digits equals datasets.load digits. This is really similar to how the iris data set is packaged inside of the sklearn thing. It's just like a good way to benchmark maybe a very simple algorithm or something like that. It's definitely not a valid data set, in the sense that like there's some discrepancies in it. I mean, if you look at a single entry here, this is supposed to be a 9, I believe. Yeah, this is supposed to be a 9, and it's kind of like pixelated and hard to read or something like that. But it's good. It's good for just testing out some stuff, kind of teaching you guys what's happening. So the first thing we want to do when we're dealing with our data set, it's stored in X and Y, is run the train test split. So we've imported this from sklearn.crossvalidation. And what we want to do is take our data and make sure it's split very nicely. So this is the first step that you always want to follow when you're dealing with this data. And what I'm doing is basically packaging everything in a training set, which I'll run cross-validation on, and then a test set which I'll hold out for later evaluation, which I'll use to like evaluate my best classifier, I guess. So XY and... Let me see, is there anything else? Oh, yeah, that's not informative. Let's see. It seems like we're good. And just to make sure that everything's dandy, I just want to make sure that I didn't mess up the order. And the way to do that is just evaluate the lengths. And so, yeah, so X train and Y train are good. So that means they're the right length. You don't have to do that step. Just make sure that the order of your variables is the same as mine. Any questions? Oh, actually, I realized I missed one parameter. So you also want to put in the test size. And all this does is basically, it just determines how much of the data set you want to be your test. So I just chose 20% of the data set to be my test. The remaining is going to be my train. And so the next thing I want to introduce you to is this thing called cross-val score. Basically what it does cross-validation for you. So we have this training set, and we want to evaluate how well we're doing with a classifier. And I'm going to start with the KNN model. So to start it out, you just basically want to type in KNN equals KNN3. So I'm just making a 3NN, 3 nearest neighbors classifier. And I want to, hold up, let me check my cheat sheet. Yeah, so I basically want to evaluate what kind of scores I can get from this. I basically want to see how accurate I can get with my training set and my test set. So I will run CLF score, equals cross-val score. Pass in the classifier, so k and n, and my training set, my training labels, and then the great thing is you can actually specify the number of folds. So basically, cross-val score does k folding for you. It's a very, very convenient metric. And what it'll do, I'm just going to use 5 for now. And what it will do is it'll basically split up the training set into 5 different pieces, run k-fold cross-validation on it, and then give you the accuracies for each fold. So as you can see in the first one, we get 97% for the first holdout test set, validation set, sorry. 96 for the second, third, fourth, and so on. And then, I mean, this is great, but we need to do something so it's a little bit more readable so we can like actually evaluate how well it's performing. And what I just basically made a function, function that takes in this this input, this array, and returns the average and the standard deviation. So you know about like how well each classifier will be doing. So as you can see, I pass in the same value, CLF score, into CV stats. I get the mean, and I get the standard deviation out. So that's just an idea of how well it would do across like multiple different validation sets. And so now we're going to use this to actually pick our hyperparameters. So the first thing we want to do is just set a variable for our hyperparameter, set it to k equals 2. And while k is less than 100, what I'll want to do is make a new k and n. Okay. Calculate the cross-val score. What is it? K and n x train y. CV equals 5. And then get out my CV stats. Add a little extra thing as well. All right, CV stats. Oh. And I think that should work. Okay, cool. So now we can evaluate the k nearest neighbors algorithm over a wide range of k parameters here. So as you can see here, the average for k equals 2 is like 98%, yeah. And same with k equals 4, and then it kind of gradually goes down as k increases. So we can probably guess that around k equals 4 is the best among all of these. But the great thing about cross-validation is not only can we determine like hyperparameters for a model, but we can actually determine what model is probably best for a problem. So we're going to do the same thing for logistic regression. And again, as I mentioned earlier, there's a hyperparameter for logistic regression in the sklearn package that allows you to adjust the penalty. So basically, the penalty makes sure that weights, the size of the weights, the magnitudes of the weights, are basically limited, or at least like subdued in a way. And so in a similar way, I'm just going to make a penalty equals 0. What's the exact value I did? 0.01. And then while the penalty is less than 10, I will make a logistic regression. Make sure you run this cell. Logistic regression and penalty equals penalty. Cool. So calculate the score. Get the stats. Print out the output. And then once again, I'm going to increase the penalty. And I don't think I mentioned this earlier, but you typically want to do something on the order of magnitude. You want to be adjusting on orders of magnitude instead of just like adding certain values to it. Because if you were adding values, you are only exploring a very limited range. But when you're going through orders of magnitude, you can explore like a huge range. And then in cases where you may have more complicated like hyperparameters, as is the case with the penalty values, what you can do is you can look for the order of magnitude that looks like the best, and then just explore the local space around that. So in this example, if it works, oh, no, it doesn't. What is the problem? Oh, what did I do? Hold up. Oh, my bad. Yeah, so penalty is a different thing inside of logistic regression. It should be a C equals penalty. So make sure you fix that, otherwise you'll run into an error. But as you can see here, it's running. And then let's say that I wanted to figure out what the best, if I wanted to go even deeper and figure out what's maybe the best penalty along this range. I can see that between 0.05 and 0.125, 0.005 and 0.125 are probably the best values. So I could change this value here. So I go through 0.005, and then maybe I would explore something like this, and I get a few values out. And it looks like the best performing one is still around 0.01, and then maybe I could just do, actually search linearly instead of geometrically. I mean, at this point, they're all like pretty close to each other. So I could pick something like, well, this is ridiculously small. So 0.011. So I can do the same thing for the linear regression as well. But there's a special kind of linear regression that can be used for classification, but it also has this penalty term. It's called ridge regression. And similar to how the logistic regression has this penalty term, it basically just limits the size of the weights. I'm just going to copy this over and just change a few things. I honestly think this should work. No. Oh, it's an alpha in this case. And this one evaluates fairly quickly, and it doesn't really seem like there's much change between any of the values. So for this range of penalty, my bad. That's why. No, just kidding. It doesn't really seem like it changes much. So ridge regression is like pretty consistent in this case. So yeah, now that we've evaluated like a pretty good range of different parameters plus like a different range of models as well, we can go through and just find which one performs the best on this data. And so if we look at ridge regression, we could probably quickly reject it because it's at like about 94% accuracy. In logistic regression looks a little bit better. It's at 96% accuracy, but it seems like K, nearest neighbors, is the best performing algorithm here. And what I'll choose K equals 4 because that seems to be the best one across this cross-validation. And now I'm going to use this holdout set that I created at the very beginning, the X test and Y test, and I'm going to evaluate how well it does. So CLF is going to be equal to KNN4. And all I have to do is just fit it to the training set, run the predictions, which is what I do right here, and then I'll evaluate the accuracy. And I get a 97% accuracy. Now this looks a little weird. If you notice here, this accuracy is actually higher than the training accuracy. This normally doesn't happen. So what could have happened here is that the training set is the testing set just so happens to be a little bit better and more comparable to the general, like to the training set as well. And so something we could do to remedy that is basically just playing around with different permutations of the training set. Let me do this. So what I did actually to make this a little bit more consistent, so you guys got pretty much the same results as I did, I set a seed. And so maybe I could just remove the seed by just setting np.random.seed, run that again, and then, accuracy still stays high. So this could also be a problem with the size of the division of the training set as well, the size of the division between the training and the test split. So you could do something like that. And I want this to work. Whatever, don't worry about it too much, but this is like a toy data set, so it has some weird inconsistencies, but normally you'll definitely see a test set or a test accuracy that's much, much lower than the training accuracy. As you notice here, though, this seems like a lot of steps to just figure out whether the classifier works, and it turns out for scikit-learn, they actually are. You don't need to do all these steps. So the key things that you do need, though, are the clf.fit and the initialization of the classifier. But to actually do all this stuff right here that I've highlighted right now, you actually can just run this one step. clf.score, x test, y test. Really easy, it gives you the exact same number out. And you don't have to kind of calculate all this boilerplate. So for a lot of different classifiers and regressors, there's a bunch of different loss values or accuracy values you can use. And so this is just a really easy way to grab those and use what is probably the best practice for that specific classifier. And then I'm going to take a second to talk about confusion matrices. I'm not sure if we've actually brought them up in this class yet, but if we haven't, then it's kind of a good opportunity to learn what they are. And so they're stored within sklearn metrics, and what they allow you to do is basically determine what kind of mistakes your learned model makes. What you guys may have heard of before is this idea of like false positives, false negatives, and true positives, true negatives. So what a confusion matrix does, it extrapolates that idea to not just like a two-class problem, but to like an n-class problem. So in a two-class problem, you'd probably make like just like a 2x2 grid, where you'd have your like where on the y-axis you would have your predicted class, and you'd have your x values as your true class. So in this one, this cell right here, the top left cell, would be your accurate predictions, your true positives. In the bottom right class would be your true negatives. The most left and most top, the left column being the true positive, the true class positive values, and the top row being the predicted class positive values. So I can elaborate a little bit more on that if that's a little confusing. I don't know, nobody's raising their hand, so I guess we're okay. But in these remaining cells, these are where you've gotten it wrong, where your predictor has messed up. So in this bottom cell right here, you're getting a false negative, and in the top right, you're getting a false positive. And so depending on the problem, you'll probably want to weigh for one or more of these, because in reality, you can't escape either of these problems. Like, you're going to probably face issues where you get false negatives, false positives, and everything like that. But in the case of a disease diagnosis, you probably want to weigh towards the side of false positives. So you want to make sure that you're not predicting that somebody's healthy when in fact they're not healthy. You want to instead probably predict some people as sick when they're not sick, so that maybe they could spend like a few $1,000s of like extra diagnosis. So say for cancer, like let's say you're diagnosed and or you're diagnosed preliminarily, then they could run like a more expensive test like a biopsy or something like that, remove what they think is a possible tumor, and from there they could determine that, oh, it's probably not cancer. But you don't want to like remove tell somebody from a preliminary exam that they don't have cancer when in reality they do, and then like 6 months later they end up dying because they didn't get the proper diagnosis at the time when it mattered. However, the opposite may be true as well. So in the case of spam classification, you typically want to lean on the side of false negatives. And this is because you don't want to put somebody's important email in the spam folder. You don't that could be something that actually matters in their lives, and doing so would hurt your company as an email provider. So yeah, we can generalize this to the end class case, which I'm just gonna skip through all this stuff. It's just plotting. If you really want to read through it, go ahead. But for the most part, you can just copy paste this. And what I'm gonna do this on is the predictions that we received from this KNN classifier up here. And as you can see, because this is a toy data set and it's pretty easy to figure out, we did pretty well. So these, on the y-axis are the true labels, and then on the x-axis are the predicted labels. So I actually flipped it on that example, but I think you guys get the idea. So as you can see on this diagonal right here, this is where the predictions are correct. These would be our true positives and true negatives. But I mean, in the 10 class case, where the classes line up. So the idea of positive negativeness kind of deteriorates here. But you can kind of see the similarities here. But then all these other cases right here are where our classifications are incorrect. So in this cell right here, we see that our algorithm predicted that this digit, which is actually a 5, was a 4. And this digit right here, which is actually a 5, was a 6. And although this algorithm does particularly well, you'd probably imagine in an accurate case you get something pretty crazy with a lot more overlap in these areas. And that would just give you an idea of which parts of the data set or which labels your classifier is particularly failing on. And so maybe in the MNIST data set, which is a little bit wider and bigger digits and has a little bit more room for error, you could probably expect that in a naive classifier, you maybe get some confusion between a 7 and a 1. And so this cell right here will probably be pretty high. Same with this one down here, the intercept between, or the one up here, the intercept between 7 and 1. So you'd expect those cells to be pretty close to to be pretty heavily populated. But you could probably also expect something like, what would be pretty different? Probably a 3 and a 9 would be pretty different. So you expect the interception between the 3 and 9 would be pretty low, and so on. Does anybody have any questions about that? Cool. Yeah, so the next thing I want to go over is just kind of a quick review. So that's pretty much the end of the cross-validation stuff. If you guys want to talk a little bit more about it, please come to me after class. And what this is just going to be a simple review of all the different models we've talked about in this class. So we've explored 4 different kinds: linear regression, logistic regression, k-means, and k-nearest neighbors. So the first thing is linear regression. Just going to be importing stuff as normal. And it's a pretty simple model to initialize. You can just do CLF equals linear model dot linear regression. The reason I do this linear model is because I've imported linear model instead of instead of something like this. Just kind of keeps it a little bit more organized, and in our case, it reduces the number of imports we have to make. I mean, the choice is really up to you. It's not a really big it's not a very important choice to make. So the first thing, so we just initialize it, and then we'd want to just fit, and we have our X train and Y train data set, or data sets, and then that should be all good and dandy. And now we want to predict or see how well it does, and we can just do the clf.score stuff that I mentioned earlier, because every single sklearn model has this API attached to it. So we just do that, and we get an idea that it has about a let me take a step back. So this scoring right here is a little bit different because it's unlike the accuracy prediction with the classifier situation. You can't exactly compare the 2 different linear regression values without running into problems, because if you try to just determine whether they're right or wrong. There's just a whole range of values that could be wrong. So instead, you need to take this statistical number called the, what is it called? I can't remember the exact name of it, but it follows this formula where you take the difference between the actual value and the predicted value, which is this f of xi, and then divide that by the actual value minus the mean of all actual values. So that's what CLF.score, linear regression.score will give you. And what it essentially means is that the closer you are to 1, the more accurate your prediction is. And, whoops. So what I've done here is I've basically just shown you what happens when you run the accuracy measurements on the training set and the testing set. And this is really weird. I guess it's the same thing that's happening before, but I bet if we mix it up, yep, we get something a little bit more expected, where the training accuracy is higher than the testing, is higher than the testing accuracy. And 9 times out of 10, you're probably going to see that in most of the models you'll experience in the future. And that's where randomization comes into play again. So as you saw, I just reran this, and it showed that I got a different value there. So just make sure you run a few randomized tests whenever you're evaluating your models. And and just to kind of show you how linear regression graphically does everything, we can just run clf.predict for x test. So this is just for the test set, and you see that it kind of approximately follows this line. I'm not really touching on the data sets that much because they're not that important. They are just toy data sets, and they're specifically made for specific tasks. So this is like Boston house prices. You can expect that a lot of them are kind of fudged to work better for certain problems. So I wouldn't worry too much about the specific sklearn data sets. Does anybody have any questions about linear regression? Cool. So I'll move on to logistic regression. So very similar to linear regression, except for it's like not actually a regression. It's more of a classification problem. It's a weird misnomer that's kind of stuck with the world of stats and machine learning at this point. So just deal with it, I guess. But let's see. The initialization is really, really similar. I'm honestly just going to copy it. Let's see. And then just make sure that you change linear regression to logistic regression. And as we've changed xtrain and ytrain, we're setting it to this new data set that I've provided. So this is a cancer data set. It's a bridge from another breast cancer data set that's located in the UCI data set repo. Just as a side note, if you guys want to look for random data sets to play around with, you can go to the University of California Irvine Machine Learning Repository, and they have a bunch of data sets available there. You can download them, and then you can do a bunch of different tasks on them. They also link to all the papers that have used them and cited this specific data set, so you can play around with their code as well. See how well they performed against a specific task. And back to this. So we've initialized our data set, we've loaded it into our x and y, and then we've made it into our specific train test splits. Now let's set up our classifier, our logistic regression classifier. We fit it, and it gives us this output of what's happening inside of the linear regressor. And now we want to evaluate how well it does. Let's call our score. X test y. Oh, sorry. This first one's going to be for our training accuracy. Cool. And as you can see, the training accuracy and test accuracy are as expected. Training accuracy is higher, testing accuracy is a little lower. And second to last is k nearest neighbors. So as I showed before, k and n, whatever. And I'm just going to use the same data set. X train, y train. And you know what? Nah, this would be easier if I just do this. Just going to cheat again. Just copy all this stuff. And make sure you run everything. And bam, you get a training accuracy, testing accuracy as we'd expect. Cool. So The final thing I'm going to touch on is k-means, and just as a note, k-means is not a classifier. It's really confusing that there's two classifiers that start with k, but k-nearest neighbors is just looking for the points in the data set that look really close to it. K-means, on the other hand, just is an unsupervised learning algorithm that just tries to find like an inherent structure inside of the data itself, and you set the different possible structures as the parameter k. And so what I'm doing here is I'm making another toy data set. It's actually a generated toy data set called blobs. And it's specifically made to evaluate some clustering algorithms. So I load the data set here. I want to set up k-means, and we can do that by CLF equals k-means. Let me see. So n clusters equals, wait, let me check this. Okay, yeah. So make blobs is set to, actually, I'll just add that in. Centers equals 3. So that just basically sets the number of possible blobs as 3. And then k-means just, we initialize the number of clusters as 3. We want to fit the data. So we just do CLF dot, ooh, that's no good. Nope. And that's why you should probably just press tab whenever you want to type in anything that's in the parameters. And CLF.fit should give you this output. And then what I'm doing here with the prediction is basically just getting out the different assigned cluster values for the data set that we're passing in. So we're not strictly adhering to training test set because we're actually not really dealing with a supervised learning problem at this point. And as you can see, we plot it, and these are the different classes according to our k-means classifier. And if you look graphically, like this is clearly its own class, this red is clearly its own class, and this green is clearly its own class. So I mean, and all these other points are a little bit unclear, but it doesn't really show, and you could probably guess that they belong to this specific blob. Yeah. All right. Any questions? Cool. Yeah, I think that's everything that I had prepared for you guys. Yeah, if you guys want to work on your projects now, you feel free to do so. I have to leave in about 5 minutes, so if you need to talk to me, do so in the next 5 minutes. Cool.